So we are working on 11.4a, problem number 15. The right hexagonal prism shown has regular hexagons as bases. And notice when you have a prism, you name it according to what the parallel bases are. So our bases are hexagons, so that's why it's called a hexagonal prism. And it also tells us that those hexagons are regular, giving us the clue that all the sides are the same length and all the angles are the same length. And we are supposed to, for part A, name all the pairs of parallel lateral faces. So that's just talking about the sides. The lateral faces is talking about the sides, and it wants us to give the pairs that are parallel. So they're going to be opposite each other. So, for example, the face AB, B prime, A prime is directly across from ED, D prime, E prime. Does that make sense? The ones that are right across from each other are parallel.
Mhm.
Susan,
Yes.
does that help?
Yes.
For part A, you're just naming those opposite sides. Go ahead, I interrupted.
So would it be wait a minute, what is E, D, and E prime and D prime?
It's just another.
That's just the back one, right? And it's parallel to A, B, and A prime, B prime.
Yeah, you need that when you say it, you need to give them in order. So A, and to name a plane, you give 3 points. So you could call it A, B, B prime is opposite E, D, D prime. Does that make sense?
Sort of.
So do we have to name the planes? Because when I checked it in the back, it doesn't name the planes. It just says something funny.
Yeah, in the back, it just says there will be 3 pairs of parallel faces.
Yeah,
By
that's what it
any
said.
3 pairs of opposite sides of the hexagonal base. So they didn't name them. There's so many ways that you can name them, but it's the ones that
Okay.
are opposite each other.
Okay.
And that's because we've got regular hexagons. If you actually looked at a regular hexagon, I'll do that. I'll pull it up in GeoGebra. That might help us to see the parallel sides.
While you're doing that, can I ask a question that
Yeah.
I feel like it seems like a dumb question, but I just don't know. So why would they be, those letters would be prime instead of just giving them different letters?
They were trying to show the relationship, like E and E prime are both in the back. They're along the
Okay.
same plane, and D prime are also in that same plane. So it just helps see the relationship better. They could have called them A, B, C, D, E, F, G, H, I, J, K, L.
Okay, thank you.
Mhm.
So if you were going to write it, how would you like write the plain part, the letter part of it, I guess?
Make it much.
Here's an option. You could have said, like for the front plane, you could have called it plane A, B, B prime is opposite plane E, D, B prime.
Okay. Do you put the little parallel lines in between them? The little slanted lines.
Just saying name the pairs. So I put a comma here. I
Okay.
need a pair. It's one of the pairs.
Okay.
Okay, I'm gonna click on the regular polygon tool and put on 2 points, and I'm gonna tell it that I want 6 vertices. So there's my hexagon. Now, can you see right here that the opposite sides are parallel in the hexagon?
Yes.
Forgot.
So this problem is just taking it into that third dimension. And instead of just looking at the parallel sides, you've got parallel faces. If I can do this and make it look three-dimensional, I think I can. So I can connect C with C1, or you could call it C prime. B with B1. A with A1. F with F1. Letting me. B with B1. B with B1. So now you can see, so right here on top, this face is parallel to the back face. And then you've got this right-hand face, the B, B1, C1, C is parallel to the F, F1, E1, E. And so on.
Okay.
The planes are parallel. Okay, now the next question here is, what is the measure of the dihedral angle between two adjacent lateral faces? So I think that it would be an easy one to look at would be like looking at this face right here, FA, A prime, A1, F1, compared to this face, F, F1, E1, E. So we've got those two faces that are right next to each other. And we want to know, what is this angle right here? Do you know any formulas that could help with that?
Hmm. No, off the top
Oh,
of
is
my
that the
let's look
180?
again.
Is that the 180 parentheses n minus 2?
We've got 6 sides. So we'll have n is 6 minus 2. So this formula, the 180 times n minus 2, is going to give us the sum of the angles in that hexagon. But we don't want just the sum of the angles. We want that exact individual angle. So what should I divide by?
6.
6.
Yep, there's 6 angles. So divide by 6. Division by definition means you're breaking into equal parts. So that will give us 120-degree interior angle of that hexagon, which, because we're in 3D, is the angle between these two faces right here as well. Because you really could slice a parallel plane anywhere along that hexagonal prism, as long as that slice was parallel to the bases you could find that 120-degree angle at any point.
Could you also look at it like the whole thing would be 360 degrees around it and then divide it by how many sets of faces there are?
Like if you were looking at this point, 360 degrees around that point, is that what you mean?
Around the whole thing.
The whole hexagon?
Yes.
Oh,
Okay, if you're doing that, you could look at like this, if you extended segment BC, if you extended that and you looked at that exterior angle, and then you extended CD and looked at that exterior angle and did that all the way around, yes, if you added all those up, the sum of those exterior angles would add up to 360, but that's not going to help you in this problem.
Okay.
But that is an interesting property that with your polygons, if you add up your exterior angles in your regular polygons, they'll always sum to 360. Even if you have a regular pentagon or a regular heptagon, triangle, a square, an equilateral triangle, a square. It's a really interesting property. And that's because you're going around a circle. Okay, any other questions about this problem? Again, that was number 15 out of 11.4a. Okay, who is next?
Diana?